So how are people doing today? Welcome to the last class of the semester. So you may have other classes later in the day, but for us, this is the end, except for the final exam. Make sure you take that. I guess we'll begin as we normally do. I'll make some procedural announcements, but they're the ones that you would sort of expect to hear. I don't think anything is due either today or tomorrow. If memory serves, that all ended last week. The final exam is now open. There is a link under a course module called Final Exam. When you go to it, you can enter and take the final exam. So it's open this morning. You can take it at some point before this Thursday at 5 p.m. Like we discussed, I think last week, the breakdown of the final exam is sort of what I thought it would be. 15 questions. I think 6 of them are from chapters 17 through 28, 21, memory serves, and the other from 1 through 16. I don't think, based on what, so I looked at it a number of times, I don't think you're going to be surprised about the content of it. So it's sort of what you might expect when you look at the other assignments that you've been working on during the course of the semester. We opted this time for not the save for later option. So what you're going to have to do in that case is sit down and take the exam in one sitting. Take your time when you're doing this. It's not timed exam, so there's no rush. You don't have to finish it in like 45 minutes or even 2.5 hours. So just sort of take your time, go through the exam. On the exam, I have the option that if the internet is somehow interrupted when you're taking it, you should be able to reaccess. So if there's any kind of technical problem along the way that doesn't cover, maybe let me know. In terms of the course grades for the class, I'm going to need to go into Blackboard and classify the final exam. I need to add a column for it. And I think also maybe the most recent homework assignments, they get included in the grade calculation. If you go to Blackboard, no, deadline not tomorrow, Thursday. So Thursday at 5 p.m., not Tuesday. So deadline for the final Thursday, 5 p.m. So when you're looking at Blackboard, when you see the weighted total, this includes, I think, everything that everyone has turned in. There are a couple of edge cases that I think people made some error in submission that I need to take care of. But other than that, I think the grades are more or less in. So the percentage kind of gives you a guide about where you're at. Like I've said in the past, the final exam is not meant to, it will probably not ultimately change very much about that percentage. You should go ahead and do your best on the final, do what you can. It will tend to move grades either up a couple of points, down a couple of points, or maybe there's no change. This isn't to say that there are no stakes on the final. It sort of represents kind of a last check-in, last chance to make a statement about what you learned in the course. It is comprehensive, it's cumulative. So there were a number of questions that I thought were reasonable to put on the final from some of the earlier chapters, ones that we discussed at some point in the past. So it's kind of where things stand right now. If you have any questions about and you might, if you go to Blackboard and look at your percentage grade, if you have any questions about what that would currently convert into in terms of a course grade, just send me an email and I'd be able to answer it. I should have the final course grades in 2 or 3 days after you take the final exam. So, I usually give myself a couple of extra days in case anyone has any technical issues that they struggle with during final exam week. Sometimes that happens. But, that's about all I really have to say about that. So does anyone have any questions right now about where things stand? Okay. So I think the answer is probably no. So I guess this week I kind of had in mind, or this day, like the remaining day, I had in mind to talk about some of the material in chapter 17 through 21. I think last Thursday we covered, 2 or 3 questions from chapter 17. That's where kind of a lot of the lift is done with significance testing. I'd like to do a couple of more problems, a few more problems today, give people a chance to work at things, like work at some of these in groups, come back, make some comments about the problems. If only to sort of demonstrate how Statcrunch might be used to come up with at least some answers. And then toward the end of class, I think I probably want to just sort of address questions as they come up, maybe more naturally if people have things they want to talk about. We might have 20, 25 minutes left in order to do that. And then that's sort of how I imagine things will go. So to that end, I'd like to, I'd like to be able to use the book to motivate some of this, or at least to give you some questions that I think might be reasonable. So I'm going to go to the Pearson e-text, which I think now you can see. So there are a number of problems. I've got maybe 3 in mind. One from each of the last 3 chapters that we discussed that will be on the final chapters 18, 20, and 21. I'd like to start with this problem 43. So take a few minutes to open the ebook and look at problem 43. I'll break people into groups. The problem, basically in this particular problem, I mean, what's embedded in it is the idea that you need to be able to formulate some kind of statistical set of statistical hypotheses concerning this question, question A and B, and then B is more about like thinking through, the content of what's been said here. I think B, when you formulate the hypothesis and then run some tests using Statcrunch, that stuff is sort of automated. I'd like to think a little bit more about B. What I would say is on this problem, B is more related to the conditions for inference, and in some sense, I guess, common sense about what it is that you're actually looking at here. So that's the first problem I'd like the groups to consider. It's about 103. Let me break people into groups. Let's take about 7 minutes to do this. That's 6 groups. So let's meet again at about 1:10. I'll make some extended comments. Groups can get a chance to mess with the problem a little bit. And you can get some practice in using Statcrunch, and I'll go through the resolution of the problem, at least on Statcrunch, and make some additional comments, I think, on B. So I'll open the room. So you have the invitation. So right now, I think probably let's meet back here at about 1:11. So welcome back. So when thinking about this problem, I mean, there are a few rather odd details about this question. I mean, first of all, the movie itself, I forget exactly when it was made, but it has to be at this point like 70 or 80 years ago. Shortly after the United States began to, mass produce atomic bombs. And so, it was filmed in the desert, not too far away from where some of these were test detonated. And as the problem says, the radioactive fallout sort of drifted over. It was known that the fallout drifted over the shooting location. And so, you would wonder whether or not there were any effects of this. The problem describes some sort of high incidence of cancer among the cast. Doesn't really mention, or in the crew of the film, maybe it's unusually high. Maybe this makes one suspicious that that there's something going on with a relationship between exposure to radioactive fallout and the development of certain cancers. So that's possible. You can't rule that out. And I think a lot of people today at least believe that. But I guess when the film was made, people weren't thinking about things that carefully. There are a couple of other issues I think I'm going to bring up when we talk about part B. But I'd like to be able to treat part A by just formulating the question as formulating the question in a way that is compatible with what we discussed. So there are a couple of things I guess you could do when you're thinking about problems like this on 42. So let me you have 46 out of 220. That seems high. It's only 30 that you would expect out of 220 according to the experts. So on this problem, we'll let P represent the true proportion of people in some population who get cancer. Now, the population is, or I guess, die from cancer. If you look at the problem, So one question that you can ask, I think, here is what population is it that we're at? I mean, what is the population we're actually considering? And that may be important for question B, but if you're proceeding just directly through some kind of calculation, you're formulating hypotheses, you're thinking about what the data suggests, you know, the null would be, you know, something like this, which if I remember right, see, I did the calculation on Excel just a minute ago. That's something on the order of, let's just say 0.136 for the sake of the problem. It's pretty high. And the alternative is that, you know, looking at something greater than what we're seeing in some general population. So, you know, something unusual is going on. So this maybe, you know, the way that we're formulating the problem here, you know, we may want to think about this when we think about part B, which we'll do in just a second. We get a point estimate. I guess, you know, we can, you know, die from cancer. So I guess I should write here, is this really, you know, how we want to characterize P? Think about that in just a second. We have a point estimate for P. So I think, I mean, like, I guess I'm suggesting more work needs to be done here, but we have a point estimate for P, and that's 46 over 220. 220 people working on the film, 46 of whom ultimately die of cancer, compared to, you know, a null hypothesis when we're thinking there's nothing particularly unusual about this population, about this 136. So in this type of problem, you know, one would typically use Statcrunch in order to come up with some, you know, you'd work out, you would think about running the statistical test through Statcrunch. And since we're dealing with proportions, that's the thing to look at. So you go to stat, proportion stat, one sample. Now in this case, we don't have the actual data, but we do have a summary of the data. And the success in this case, I think we were thinking about being someone who's died from cancer, which is an unusual, kind of an unusual thing to call success. If we're running hypothesis tests, you know, what should P be? In our example, I think we're thinking about this being about 0.136, and it's a one-sided test. You're trying to think about whether or not you're running into anything unusual. So how many standard deviations away from this 0.136 is this 46 out of 220? And when you compute that, you know, you get a z-statistic that's on the order of about 3.16, p-value about 0.0008. So we can report that here. So in this problem, p-value is low, on the order of about 0.08. The associated z-stat is about, I think it was about 3.16. So, you know, if you happen to know the significance level that you're starting with, then, you know, that p-value will probably cause you to reject the null. A couple things to say about this, and this is maybe related to B. I don't think, so we should be careful. You know, let's be careful about what P represents. So it doesn't just represent some sort of blanket, you know, the proportion of people who die from cancer. So, and that's because the experts in this sense have already, you know, formulated what you should expect in cases like this, that the overall death rate from various cancers should be on the order of about, you know, 13, 14%. So that 46 is right at 220 is a bit high. But you shouldn't think it's some sort of, you know, general, you know, you're not thinking that this is sort of some general statement about the entire population. It's almost as though that we want P to represent a death rate from cancer for those that are somehow exposed to radioactive fallout from nuclear weapons testing or something like that. So it's a bit more complicated than I think that we originally wrote. And when you're thinking about B for a minute, you know, do you think that this represents evidence? This is part of what one objection might be, that, we weren't too careful in the original formulation about P, but if you state what P is, it represents some death rate from cancer from those exposed to radiation, maybe. Then maybe it is evidence for that particular belief that the death rate's higher, but we do have to be careful. And the reason, is this, like people working on, is the sample, that we get from the film, the sample of 220, truly random? Not really. So you happen to be having people that happen to be working on a film at a certain place at a certain time. These people's behaviors in general might be associated to getting cancer in ways that, for certain behaviors that are not shared by the general population of people living at that time. For example, the problem is framed by, this initial discussion of the movie actor John Wayne. John Wayne smoked a huge number of cigarettes, and eventually I believe he died of lung cancer. So it's probably not surprising that he died of lung cancer. It was known even then that smoking lots of cigarettes probably made you more likely to die of cancer, or lung cancer specifically. So, was it the radiation in his case, or was it all the smoking? I don't think it's so clear. Probably the radiation didn't help, but it may not be, it might have been the same for him either way. And so, and that may be true for many people working on the set, but of course, people at that time smoked a lot. And maybe people that worked on film, due to the nature of the work, might have smoked even more than people not working on film. So maybe they were susceptible to cancers or at least cancer at a greater rate than the general population. So one thing that you should question in this example, I think, is the randomness of the sample. Seems to me that that's something that if you're trying to use this as a piece of evidence in favor of a certain statement about radiation, it would be difficult, it would be something where, well, of course, maybe we should still look into it. So maybe, we'd look into the relationship. But again, I think this is a problem based on this. But you need to know more. And I think the issue with radiation, I think it's probably pretty well established that it has the effect that the problem is trying to describe. But this is based on quite a bit of work, and there are also, I think, theories outside of what we're doing in statistics, which might explain why something like a higher rate of cancer for people that are exposed to radiation might be expected. So when you're thinking about this type of problem, you have some evidence, but you probably don't necessarily believe that. If you do believe that radiation might be related to the formation of cancer cells, you probably don't necessarily think that's true because of this one incident. Maybe it's not surprising to learn that people that were exposed to radioactive fallout on a daily basis for quite a while develop cancers at a higher rate. You wouldn't be shocked if someone told you that. And maybe there is some sort of relationship, but all I'm saying is that there could be other things which also kind of could cause this. So if you're thinking about this type of problem, it might point you in the direction of a certain belief, but in order to sort of establish that or begin to establish it, you would probably need to do a little bit more work. You'd probably need to deal with this kind of thing right here, developing some random sample and doing a more careful study. That would probably be necessary in this case to establish some linkage, if that makes sense. Some of the other conditions for inference, I think, are actually okay. If you take a look at like the success-failure condition, there's no real problem there. P time, the presumed value for P, 0.136 times 220 is 30. So the number of expected successes is 30. The number of expected failures is 190 under the null. So success failure seems okay. So the sampling distribution under the null would probably be reasonably normal. So the techniques of inference, I think, would be fine to use. Mathematically, it's fine, but it's just these other somewhat non-mathematical issues that I think you'd probably be a little more worried about if you're trying to use this as evidence. So does this conversation make sense? This is always the way it is, actually. If you look at papers, there's almost never, you know, when you're looking when you're looking at a result that's like surprising or unusual in some way, it's almost never, you know, well, okay, look, I used the statistical software, it came up with the wrong number. I mean, it happens sometimes, but that's pretty rare. It's usually in, you know, what people are trying to do with some data that they have. I mean, what they're trying to infer based on the data. Other things you can do here, you could construct a 95% confidence interval. Statcrunch will admit that as well. So let's see how to do that. So if you go to Statcrunch, we can always edit this. So instead of running hypothesis test, we can come up with a confidence interval. And if we do something like that, we get the upper and lower limit automatically. Lower limits on the order of about 0.15, upper limits on the order of about 0.26, 0.27. The important thing here, excuse me, is that it doesn't contain, you know, it doesn't contain 0.136. So again, confidence interval construction like this is equivalent to some two-tailed test, but at least this represents some evidence kind of in the direction that you kind of already kind of believe. If you look at the data, you're getting a confidence interval, which is quite a bit to the right of, you know, the value 0.136. So you have something that represents evidence against the null hypothesis, if that makes sense. You know, so the inferential methods, you know, all tend to want to support each other. In cases like this, you get results which are sort of unambiguous in one direction. So you do this way of organizing the evidence, I guess. But, you know, again, whether or not you should think that this is terribly strong evidence, it's a question about the randomness of the sample, I think, in my view. So again, you know, probably not a random sample. Probably you'd have to do a bit more work. So does this make sense? All right. So some more questions, I guess. I have in mind a couple of more. The next one is from the chapter 20, page 640. Yeah. All right. So let me bring up the screen, and we'll sort of proceed in the same way. We'll try to formulate the problem statistically, and then see what kind of results we get. So this question is from chapter 20. In some sense, that gives you a guide about what kind of problem it is. But I'd like you to put that out of your mind for a minute. Think a little about 48. So it's question 48 here, where you're dealing with a poll. You're talking about carbohydrates. If you try to avoid carbohydrates in their diet. Gallup poll is a pretty good pollster, so you know a lot of the things that you would normally worry about for this type of thing probably aren't going to worry about there. You do feel like it's a random sample. The sample size is rather large; it's 1,005. So we're expecting a fairly, you know, if we do the work through by looking either at a confidence interval, we expect it to be narrow. Margin of error won't be that big for what we're trying to do. I'd like the groups to think about 48, and you know, when you're thinking about question 48 as groups, when you're considering this problem, again, you know, you're thinking about, you know, you have a summary of some poll, and you're trying to figure out what sort of evidence, you know, whether or not you have evidence for something, right? And if so, what? You know, and also probably on questions like this, you know, is there a way of not getting evidence for something? Well, we can talk about that in just a second. So it's problem 48 here on page 640 that I'd like the groups to consider. Right now it's about 127, I think, like we did last time. Let's just, in groups, take a few minutes, take about 7 minutes, 8 minutes. So we'll meet about 1:35. We'll go through the problem. At minimum, we'll sort of describe how to do it, use Statcrunch to maybe think about it a bit. So now the rooms are open. I'll see you in a few minutes. All right, welcome back. So to continue the discussion that we're sort of, you know, that we're having about these inferential methods, I think what you're seeing here on 20 is a slightly different inferential method than the one you saw earlier. In particular, I think on 48, you're still talking about proportions, but it's not, but it's not a question of, you know, looking at one proportion against some fixed number. It's looking at a gap between two proportions. So you're dealing with proportions in 2002 and proportion recently. So let's say, if you take in this book, if you think about its publishing date as being maybe 2018, let's just take that as being recent. So the question is, you're trying to measure something about the proportion of adults that try to avoid carbohydrates in the diet. That number increased to 27% from 20% in the 2002 poll. So it looks like there is a difference in proportions. Question is this a statistically significant increase? And we'll try to analyze this question from that point of view. A couple of ways of doing it. One way of thinking about the problem is the, I think this is 48. Let's formulate a set of statistical hypotheses, and let's at least keep track of what these things are meant to measure. So first of all, let P 2002 represent the proportion in the population of people who avoid carbs in the diet. And let's just take for granted that the book publishing date is 2018, recently. Well, I don't know if it's easier or not. Yeah, recent. Let P recent be, whatever you imagine the year of publication of the book being, represents something similar. For now, for the present time, the present moment. So, once you've decided, at least the names of the population parameters that you're considering, what makes sense to do. So we notice that P hat recent is 0.27 and P hat 2002 is 0.20. So it looks like things have gone up. The question is, did they go up enough for you to regard? Have they increased enough? So is this change significant from the statistical standpoint? Now, in a problem like this, it's useful to kind of adopt a significance level, I think, at the outset. So let's just say that we use a significance level of 0.05 for what we're doing. So that's the level we'll use. We'll formulate a null and an alternative, which kind of makes sense given the problem. I'll subtract. I mean, in the order of subtraction in this case, sort of matters, but let's take the subtraction to be in the direction of recent minus 2002. And the uninteresting hypothesis is there is no difference, even though there's some we're thinking about what we're saying as just being a feature of the sampling variability. The alternative is that there's a one-sided difference. So my belief in this problem is that, the good interpretation here is we're thinking about whether or not there's an increase. And so it makes sense to formulate the problem as a one-sided test rather than as a two-sided test. We're not looking for evidence of a difference. We're looking for evidence of, say, a directional difference. We're looking at whether or not there's evidence for the belief that there has been an increase. So we have a point estimate of the difference. That's 0.07. And so we have a sample size, and we can sort of proceed. We can proceed using Statcrunch. Do we need to know any more than this to do that? So let's find out. So let's see. If you go to Statcrunch and then try to get it to run the test, you go to Stat. We're dealing with proportions, but it's two sample, or not three, two. Proportion stat, two sample. We basically have a summary, but the problem that we have if we're dealing with Statcrunch is that we can't just put the proportion in. We need to be able to talk about successes versus observations. Now, for both samples, we're sort of led to believe in the problem statement that the number of observations is 1,005. We'll be subtracting in the direction of recent minus old. So it's going to be sample 1 minus sample 2 using how Statcrunch formulates things. The problem is I need to know the number of successes. So for that, what I'll do is I'll just go to like Excel or something like this, and I'll very quickly figure out what's going on here. So 271.35, so probably there was some rounding. Let's use 271. Kind of minimizing the difference. And for the second sample, we'll play the same game. 20 times 1,005, we get 201 on the nose. It's pretty convenient. And so what is it that we actually want to look at? Well, the way that we formulated the problem, just as a reminder, we're looking at, the null is that there is no difference, even though, the point estimates differ by apparently quite a lot. And the alternative is that there's evidence for, say, a difference in the positive direction. What I would say here is that sample size, before you really begin to do the analysis, you should actually think you do have a significant increase. One reason is that sample size is huge. And so when you're looking at a sample size like this, it's pretty unlikely that the difference of the proportions will be that large in the relative sense. Standard error in this case is not very big. And we'll see that in just a second. You can use Statcrunch to come up with a significance test. It's a one-sided test. Notice that what you see right here is a mirror of what you wrote down. You hit compute, and you get something that looks like this. Here's the printout. How do you interpret it? Well, you're seeing, as we thought, the standard error is pretty small. It's not big. You're dealing with a measurement. You're dealing with a measurement of differences that's quite a few standard errors away from zero. You've got basically a z statistic in this case on the order of about 3.68 and a very small p-value. When Statcrunch reports something like 0.0001, you usually would interpret that as being small. So based on all of this, what you'd say is that since p-value is around 0.001 and the chosen level of significance is 0.05, we reject the null hypothesis at a level of significance of 0.05. So yes, there is evidence, statistically significant evidence of a difference at the significance level of 0.05. So these are the same ways of sort of saying the same thing over and over again. So that's kind of how you approach the problem, at least from this point of view, if you want to run the test. There are some other things you can do, just like with the previous problem. You can use Statcrunch to come up with a confidence interval to sort of see what the quote unquote effect size is. You can actually just use confidence intervals for most things to sort of organize the evidence if you want. The test will force you to do some, significance testing. And I would say that significance testing is usually included in a course like this because it's a pretty common thing you see. So it's kind of good to be conversant in it. But, in some sense, interval estimate and significance testing, these are kind of equivalent methods of inference, though maybe it's not so obvious. So at this point, does anyone have any questions? So, there's also this issue, I guess. One thing that I would say about this, one kind of relief in this problem is that since the polls are being run by kind of a reputable polling outfit, you're not really worried about some of these other issues. You feel like the conditions for inference will probably be satisfied. You don't really have to spend a lot of time addressing that. Gallup will do things in such a way so that it's not, going to wind up being some kind of weird disaster where you're dealing with a fairly small sample. You're dealing with maybe 1,005 people that are randomly selected from the larger population of Americans that are being studied. You can kind of already tell that things like the success failure condition for both groups is satisfied. You're not worried about randomization. You can check these things if you want. And it's probably worthwhile doing just to make sure that you can kind of remember the conditions for inference. I think that there's a question or two on the final where you actually have to address that, if only because, you're trying to convince yourself that the techniques for inference are appropriate to apply. So in any case, that was the question. So does anyone have any questions or comments about this 48 difference in proportions? What I would say, I think, on the exam is that, if you're thinking about what we're doing with differences, you can also look at differences of means or mean estimation. We haven't done that yet. We'll look at something a bit later, in which, like next, where means are involved. But we haven't really done anything with means, at least today, up to that point. But you'd be aware that that could be on the test. Chapter 20 was kind of a catch-all chapter in which differences or group differences were examined in some detail, but it was differences in proportions and differences of means which were featured there. So just be aware that that's there. Any questions or comments or concerns? Okay. Meredith, yeah, the sample size for yes, you can. So there's a question about the sample size. Yes, assume that it's the same. Assume that the two sample sizes are the same. It says similar. It doesn't really say, but it's for the purposes of the problem, it's adequate to do that. Usually, the author of the question is probably going to be a little bit more careful about writing what the actual sample size is. One thing about these problems, I guess, now that the question is in the air, sample sizes, when you're looking at differences of proportions or means, if you're dealing with independent groups, and that's what we're handling in that sort of situation. But again, why? Because you're thinking the 2002 group and the 2018 group don't really have anything in common. You're thinking about the responses of the groups being guided by individual concerns at those different moments. Sample sizes, when you're dealing with two independent groups, don't have to be the same. That's contrasted with things like paired data, where you have a very specific violation of the independent group assumption. But with paired data, it's a violation that we're actually capitalizing on because we're kind of looking at group differences. So just be aware that that's out there. The last problem, I think, if no one has any major objection, this question, I think, from chapter 21 involving group differences. So let's see, I've got a question right here. This question 32. I realized that my camera is not on. Hang on, my screen's not being shared. Okay, so I'd like the groups to just consider for a few moments this 32. You have a test of tires. Test is running using the same set of tires on both dry and wet pavement. You're looking at, you're trying to figure out something about how long it takes for the car to stop. Mean dry pavement stopping distance. And then you're looking at comparing A and B, the mean increase in stopping distance on wet pavement. So you've got basically in a table like this, you're in a situation where you've got the same car with the same tires generating two different measurements. And so what I would say about this is this has a very different feel than the last example. And so you're trying to look at some differences here. It's a group difference, I guess, but the groups are very much not independent because it's the same car in this table that's generating the measurement on the left that is generating also the measurement on the right. So I'd like the groups, maybe it's about 147. I'd like the groups to consider this for a few minutes, not that long. We'll get directly to it. This is an example where you have the data in Statcrunch and we can do it pretty quickly. Maybe only take 2 or 3 minutes to do it. Try to think about the conditions for inference. There's usually some 1 or 2 things you have to check here. So I'll open the rooms, take maybe about 5 or 6 minutes to think. Yes, Lily.
So wait, where can we find the data that we can load into Statcrunch? Do we just copy and paste it, or is it
definitely not? So let me show you the book. When you're close that. When you're looking at the book, when it says SC right here, you should be able to sort of wave over that with a thing that looks like a hand, and when you okay. And so when you select it, I think the data will load, and then you can kind of use Statcrunch to think a little bit about it. Now, there's several things to think about, like even for both A and B. Usually when you're looking at means, there's sort of a couple of important things to consider. Maybe one thing to consider in this example is whether or not it's plausible that, you know, the data comes from some normally distributed population. We're not really doing a very careful test there. I think in subsequent courses, you're usually a little bit more careful about that. We're just looking at histograms. So we'll play around with Statcrunch to kind of see what the data looks like in both cases, just to see if we think that things are okay. And, you know, I guess I'll leave it to the groups. Maybe work for about 5 minutes on those two problems. Let's meet again at about 1:53 and we'll kind of wrap up the discussion. All right, welcome back. So to sort of finish up the discussion here, you know, how to sort of run a paired t-test. I mean, that's in essence the matter that we're worried about here. Why is the data paired? It's because you're sort of dealing with a car with a set of tires, and these are different cars which are sort of braking, and you're looking how long it takes for them to stop, going from a speed of about 60 miles an hour to 0. You have some measurement. I guess it's in, you know, I guess it's in, right. I guess it's in feet. It makes some parenthetical comment that, you know, the distance is a lot longer if it's measuring some other characteristic. So if you're looking at stopping distance in feet, you know, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different pairs. You can load the data into Statcrunch. Now, what I'd like to spend a little time talking about here on both A and B, these are confidence intervals that you're asked to compute. We can do that pretty quickly on Statcrunch. We're going to notice that there's evidence of a difference. It's not surprising. You know, when you're thinking about the conditions for inference here, it's wise to go back and think about them a little bit. I mean, if you're running a paired t-test, I think on B, it's important to convince yourself that you're dealing with paired data. You want to convince yourself that the differences are independent, which makes sense if you're dealing with many different cars that are being tested, maybe 10 different ones, same set of tires. And so when you're thinking about this type of problem, you know, that's what's being discussed. Another issue that's worth thinking about on both A and B when you're thinking about conditions for inference, do you think on A, if you're looking at what's going on for the mean dry pavement, do you think that the measurements in the first column are approximately normally distributed? It's unsatisfying in a way to kind of discuss that because you only got like 10 elements to look at. But does it look okay? Like, do you see something that's unimodal at least? The same thing can be said, I think, on B. When you're looking at differences, you usually have to specify the direction of the difference. Choose either wet minus dry or dry minus wet. You know, but just be specific about what it is that you're actually doing. You know, when you're talking about conditions for inference, it's probably true that there's some randomization going on here. Like, well, what is it? We don't really know. It just sort of says that car made repeated stops and you're sort of randomly choosing what, right? You know, that's kind of a reasonable question. Are you randomly choosing tires out of a larger collection of the same set of tires? You know, it's not entirely clear. So there are some things to worry about, I think, on 32. You might want to make mention of those things. Typically, you know, but typically if someone's writing up some sort of study, they'll be a little bit more specific about what's being measured. I think there's some vagueness here. You know, so, I mean, is it the case that you've got 10 different cars with the same set of tires, or do you have the same car with 10 different sets of tires, right? And if you look at what's going on here, it's not clear. It's one of its tire models, so it's the same set of tires. But, you know, is it the case that you're randomly sampling 10 different pairs of tires? What's suggested, I think, in 31 is that you got cars 1 through 10. And so maybe that answers that question. But it isn't so clear maybe on 32. But there are a lot of details which are sort of left out here that are worth considering if you're really worried about the conditions for inference. I guess if you're dealing with a sample size of like 10 or something like that, I would always kind of proceed with caution, particularly when you look at the type of distribution of the samples that you get. So just for the sake of maybe brevity in this case, if you're trying to run a 2-sample t-test for paired data, you can find that under Statcrunch. Go here, look under t-stat. Notice that you have 3 choices: 1 sample, 2 sample, or paired. We've actually talked about all 3 of those choices in this class. We look at paired data here. We need to choose a direction of the subtraction. Statcrunch will default into sample 1 minus sample 2. Let's take wet minus dry. So sample 1 will have that be variable 2. It's sort of labeled in an unsatisfactory way over here, but it'll be okay. If you want to come up with a 95% confidence interval, just choose that option. One thing that's probably worthwhile is just to come up with a histogram of the differences. The histogram that you're going to see here is a histogram of the differences. So what's going to happen behind the scenes is that for each row, Statcrunch will subtract the dry measurement from the wet measurement, and then it will take the average of those. And so the histogram that you're going to see is the histogram of those differences. So let's hit compute and see what we get. So unsurprisingly, we get a confidence interval. It's entirely above 0. So we have evidence, at least, that the wet pavement and the dry pavement do matter. How do the differences actually look? They look weird. So they're almost uniform, right? So you have this, like, at least you're dealing with something that's unimodal. You got this guy right here. Maybe you got this guy right here, but that's only 2. So you're not really counting that. That's 4. That's twice as many. So, you would hope for something that looks more normal than this, but probably like the rough features of this histogram have a lot to do with the fact that you've only got 10 different measurements that you're actually looking at. It's a little annoying, so you would proceed with caution. You're not entirely sure about, what to believe, at least, about the population of differences that you're trying to perform inference on or for. So, if you had a sample of size 25 or 30, maybe it would be a little more, you'd be a little bit more satisfied with the type of status of the inference. So although it looks like there's a difference, you can't be totally sure on this basis because there may be some problems with the conditions for inference. Another thing I'd say about this, no one actually believes that there shouldn't be a difference. If you've got a lot of experience driving, then you probably realize that there's a major difference in stopping on wet versus dry pavement in pretty much any car that you can drive. And so in any case, that's kind of where we're at right now. Paired data t-test, I think that there's a problem like that on the final. You'd have to kind of see it when you'll probably recognize it. You won't recognize the problem. You'll probably recognize what it is. And so I think that's probably all I have to say in any official sense. That's sort of the review. We talked about a number of problems from 17 through 21, 16 through 21 over the last couple of days. I'd like to sort of use maybe the last 9 or 10 minutes just to hang around to see if people have any questions. If not, that's okay. If so, then hang around and ask the question. The exam is open right now. I wouldn't advise taking it right now if you don't want to, if you got other things going on. It will close on Thursday at 5 p.m. So just make sure you take it before then. And I guess that's it. I think I had a good time running the class this semester. I hope you found it to be a rewarding experience, and hope to see you around campus this fall when it becomes live again and we're not on Zoom anymore, at least not for classes. In any case, I'll see those of you that stay, and if I don't, best of luck to you going forward.